Hello everyone, I am Dipanji from BSc Chemistry Honors 3rd year. I am here to represent the topic hard and soft acids and bases. The term acid and bases are commonly or routinely used in our daily life. Chemists have been classifying substances as acid and bases since long time. Lavoisier noted that the common element in all the acids was oxygen. The word oxygen in Greek means acid former. However, Humphrey Davy showed later that all acids contain hydrogen. It was in 1884 Arrhenius, a Swedish chemist, developed the theory of acid and bases, known today popularly as Arrhenius theory of acids and bases. According to Arrhenius, an acid is a substance which gives hydrogen ions in aqueous solution, and a base is a substance which gives hydroxyl ion in aqueous solution. The strength of an acid or a base depend upon its capacity to provide hydrogen and OH negative ions respectively. The process of neutralization of an acid by a base can be represented by the reaction H positive plus OH negative gives H2O. In 1923, Bronsted and Lowry proposed a new acid-base theory. According to their theory, an acid is a proton donor, whereas a base is a proton acceptor. The acid-base reaction is regarded as a proton transfer reaction. In 1923, G. N. Lewis gave another general definition of acid-base behavior in terms of electron pair donation and acceptance. However, this theory got the recognition in 1938. According to Lewis, an acid is a substance which can accept a pair of electron, and base is a substance which can donate a pair of electron. In other words, an acid is electron pair acceptor while a base is electron pair donor. The earlier definition of acid and bases were solely based upon the observable properties such as taste, ability to dissolve substances insoluble in water, and their effect on vegetable dyes. The term acid was applied to substances that have a sharp or sour taste, turns blue litmus red, react with the certain metals to liberate hydrogen gas, and have the ability to dissolve substances insoluble in water. On the other hand, the term base was applied to a substance that have a bitter taste, soapy feel, turns red litmus blue. However, tasting and feeling chemicals are dangerous method of determining whether substance is an acid or base. You should never ever taste or touch solution of chemical in laboratory. There are however other method of recognizing acid and base. For example, acid and base that change the color of certain dyes, popularly known as indicators. One of the most common indicators is a vegetable dye obtaining from lichen known as litmus. Aqueous solution of acid turn the litmus red, whereas the aqueous solution of bases turn it blue. Thus, any substance which has an unshared pair of electrons can act as a Lewis base, whereas a substance which has an empty orbital to accommodate a pair of electrons act as Lewis acid. In other words, substances capable of donating a pair of electrons are regarded as Lewis bases, and substances which capable of accepting a pair of electrons are regarded as Lewis acid. Acid base or neutralization reaction may thus be regarded as donor Lewis base, acceptor Lewis acid reaction, or coordinate covalent bond formation reaction. Classical example of Lewis acid base reaction is that of between boron trifluoride and ammonia. Using electron dot diagram, we can see that boron trifluoride is the Lewis acid and the ammonia is the Lewis base. Lewis base plus Lewis acid donor receptor coordinate bond formation reaction. NH3BF3 NH3BF3. Lewis concept of acids and bases is very commonly used because of its simplicity and the ease with which the formation of coordination compound can be explained. In brief, all the usual ligands can be regarded as Lewis bases, whereas all the metal ions can be regarded as Lewis base. The degree of affinity of a metal ion for ligand can be termed as Lewis acid, and the tendency of the ligand to combine with metal ion can be regarded as Lewis basicity. Hard and soft acids and bases. An acid-base reaction, according to Lewis base concept, involves the reaction between donor and acceptor B to form the complex AB. The formation of the stable complex between the donor and acceptor depend upon the nature of species. It has been known since long that certain ligands form more stable complexes with the metal ions such as Ag positive, Ag2 positive, Pd2 positive, platinum 2 positive. On the other hand, certain ligands forms a stable complex with the metal such as Al3 positive, CO3 positive, PT4 positive. Based upon the preferential bonding, the acid and bases have been classified into two groups with class A and class B according to their preference. Class A metal ion include alkali metals, alkaline earth metals, lighter and more highly charged ions, Ti4 positive, Cr3 positive, Al3 positive, Fe3 positive, CO3 positive. Hydrogen metal ion include heavier transition metal of second and third transition series, heavier transition metal in lower oxidation state, low valent metal ions such as zero valent metal in metal carbonyl. Depending upon the type of metal ion, ligand can also be classified as class A or B depending upon their preference. Ligand include molecular ion with donor atom, nitrogen, oxygen, fluorine, chlorine, etc. It is important to note that the class ligands prefer to form strong complexes with class A metals. Class B ligands include molecules ions with donor phosphorus, arsenic, sulfur, selenium, iodine, etc. Class B ligand prefer to form complexes with class B metal ions. It was in 1963 Pearson coined the term hard and soft acid and bases for class A and B with metal ions and ligands respectively. Accordingly, class A metal ions are referred to hard acids while class B metal ions are referred soft acids. Similarly, class A ligand are termed hard bases whereas class B ligand are termed as soft bases. In summary, according to Pearson, class A acid and hard acid H positive, Li positive, Na positive, Be2 positive, Mg2 positive, Cr3 positive, Fe3 positive. Class B acids are soft. Class C acid, A acid are hard bases. Class B bases are soft bases. Classification of acid and bases as hard and soft. Pearson observed that it is possible to correlate acid base interaction on the basis of hard and soft acid and base. He observed that type A metal ions acids were small, compact, and not very polarizable, and these preferred ligand that were so small and less polarizable called acids and bases hard. On the other hand, the type B metal ions, the ligand they prefer appear to be larger in size, more polarizable. He described these acids and bases as soft. Hard acid preferred hard bases, soft acid preferred soft bases. Classification of acids. General classification of some common hard acids and bases along with some borderline cases is given in table. An inspection of table 4.1 reveals that hard acids have the following characteristics. Hard acids are cations of smaller size. Hard acids are cations of larger oxidation state. Hard acids are molecules cations with lesser number of valence electrons. Hard acids hold the valence electron tightly and consequently are not polarizable. In summary, hard acids bind strongly to a proton. Hard acids are small size, compact, and not easily polarizable. A close look also reveals that soft acid possess following. Soft acids are cations of large size. Soft acids are cations of lower charge. Soft acids are a molecule and with large number of valence electrons. Soft acids do not hold the valence electron tightly, are therefore easily polarizable. In summary, the soft acids are large sized and easily polarizable ions that bind strongly to highly polarizable iron molecule. It is important to note that there is no sharp division between hard and soft bases. There are a number of Lewis acids that are neither too hard nor too soft. Such type of acid that are neither hard nor soft are called borderline acid, which are shown in extreme right of the table 4.1. Borderline acid have properties which are intermediate between that of hard acid and a hard base. In case of borderline acid, the properties such as size, oxidation state, and polarizability cation molecule are neither too low or neither high. On the other hand, soft acid will show the opposite trend and order of preference, binding the donor atom with the group is observed. The above trend can be pictorially represented as complexes of type ligands, complexes of type P metals. What type of interaction do you expect between a hard and hard acid and hard base. Since both acid and hard bases are not easily polarizable, their interactions are predominantly ionic. What type of interaction do you expect between a soft acid and soft base? Since both soft acid and base are usually polarizable, the interaction between them are predominantly covalent. Classification of base. General classification of some commonly used ligand into hard and soft bases along with the borderline bases represented in table 4.2. A glance at the table 4.2 reveals some of the important characteristics of hard base. Hard base binds strongly to the proton. Hard base contain donor atom of high electronegativity. The donor atom in hard base possesses low polarizability. The hard base are not easily oxidized. Hard base contain empty orbital of high energy. In summary, hard bases bind strongly to a proton. The donor atom in case of hard bases is of high electronegativity and of low polarizability. Further inspection of table 4.2 reveals that the following features are observed in the case of soft bases. Soft bases contain donor atom of low electronegativity. Soft bases contain donor atom of high polarizability. Soft bases get easily oxidized. Soft bases are associated with empty low lying energy orbital. In brief, soft bases contain less electronegative non-metal. The donor atom in such possess donor atom that are very easily polarized, just as there are borderline acid. There are borderline bases also. The property of borderline bases are in between those of the soft and hard base. It is important to note that the categories are not rigidly divided. For example, the halide ions form a series from the very hard fluoride ion through the hard borderline chloride into the borderline bromide and soft iodide ion. The soft acid are known as class B metal ions are the group of metal ions that are in lower right portion of the metallic elements as shown in the figure 4.1. Pearson HACB principle. Pearson proposed a simple rule for predicting the stability of coordination complexes formed between the acid and bases. This rule is quite often named HACB principle. According to Pearson, hard acid prefer to a bond with hard base while soft acid prefer to a bond with soft base. It is important to note that the hardness and softness of acid and bases refer only to hard and soft interaction. It is by no mean related to the strength of acid and base. For example, F negative, OH negative ion are hard bases, but the strength of OH negative is 10 raised to power 13 times than that of F negative ions. In other words, hard acid will show the following order of preference binding of the donor atom ion within the group. Application of HACB principle. Pearson principle HACB has a number of applications. Stability of complex. We have already noted that hardness and softness of acid and bases are related only to the hard and soft interaction. Hardness and softness of acid and base nothing to do with the inherent acidic or basic strength of acid or base. For example, both OH and F negative are hard bases, although OH is for stronger base than F negative, but in fact OH is 10 raised to power 13 times more stronger base than F negative. However, in HACB principle, both OH and F ions are par with each other. Pearson in 1963 explained the relative stability of coordination complexes on the basis of HACB principle. Let us consider a general reaction between a Lewis acid and a Lewis base. Lewis acid Lewis base complex. The complex AB will be more stable if A and B both are hard and soft. The complex AB will be the least stable if A is hard and B is soft, or A is soft or B is hard. For example, a complex between a soft acid AG and soft base is quite stable in contrast one between a soft acid and hard base. Soft acid, soft base, stable complex, soft interaction. Soft acid, hard base, unstable complex, soft hard interaction. Similarly, the reaction between LII and CSF resulting in the formation of LIF and CSI constitute an interesting example, suggesting that the preferential stability of soft and hard combination. Hard, soft, hard, soft. Some of the other important reactions suggesting the stability of soft and hard interactions are given below. The rule of thumb in determining the stability of complex is the preferential formation of hard and soft interaction. Hard, soft, hard, soft. CuI2 plus CuF, CuF2, CuI. CAS plus H2O, CaO plus H2O is hard, soft, soft. BeI2, HgF2, BeF2, HgI2, hard, soft, hard, soft. Why COF63 complex is more stable than COI63. In both the complexes, COF6 3 COI3. The oxidation state of cobalt is +3, is a hard acid, therefore its combination with a hard base, which is a hard interaction. On the other hand, combination of CO3 positive with a soft base I negative will lead to COI6 3 negative, which is a hard soft interaction. Therefore COF6 is more stable than COI6. It also be noted that the combination of hard and soft ligand with the metal ion is always preferred over a combination or mixture of hard and soft ligand with the metal ion. For example, the complexes COCN5I and CONH35F are far more stable than, whereas the complex SOCNF3 negative and CONH35I3 positive are unstable. This is because Cn negative and I negative are both soft bases, whereas NH3 and F negative are both hard bases. Thank you.